Hook, what if I told you that quantum machine learning has been stuck in the same trap as early AI? Everyone claiming their algorithm is best, but nobody can actually compare them fairly. Today, that trap is finally being dismantled, and we're also going to talk about a way to do quantum error correction that feels almost like cheating, using pre-shared entanglement to make any classical code work for quantum computing. Welcome to Quantum Frontiers. And today we're diving into two papers that together reveal something bigger. Quantum machine learning is growing up. It's moving from look at my cool algorithm to here's the infrastructure to test if it actually works. First, we have MerLin, a framework that integrates photonic quantum computing into PyTorch and scikit-learn. Second, a pedagogical deep dive into entanglement-assisted quantum error-correcting codes, or eighte. That shows how pre-shared entanglement can make quantum error correction much more practical. Stay until the end because I'm going to show you why these two papers together tell us something profound about where quantum computing is headed. And it's not what most people expect. Act 1, the problem. Here's the dirty secret of quantum machine learning research. It's been really hard to compare two different approaches fairly. Researcher A builds a photonic quantum neural network and tests it on dataset X. Researcher B builds a completely different architecture and tests it on dataset Y. They both claim great results, but can you actually compare them? No, because they used different simulators, different training pipelines, different hyperparameters, different everything. This is what we call the reproducibility crisis in quantum ML. It's not that the research is bad. It's that we're all building with different tools on different foundations, making it nearly impossible to tell what actually works. The problem is compounded by something called the self-orthogonality constraint in quantum error correction. If you want to build a quantum error correcting code from a classical code, that classical code has to be self-orthogonal. That's a huge restriction. It means many perfectly good classical codes we know work well for classical error correction, simply can't be used for quantum error correction. So we have two problems. First, quantum ML researchers can't easily compare their approaches. Second, quantum error correction is constrained by this self-orthogonality requirement. Act 2, the discovery. Enter today's two papers, and they're more connected than you might think. First, MerLin. Think of it as the scikit-learn of photonic quantum machine learning. It's an open-source framework that integrates strong simulation of linear optical circuits into standard ML tools. You know PyTorch, you know scikit-learn. MerLin lets you plug photonic quantum layers into those workflows, and they're differentiable, meaning you can train them end-to-end. But here's the real power. MerLin reproduces 18 state-of-the-art photonic and hybrid quantum ML works as modular, reusable experiments. Not just their ideas, their actual implementations with a shared baseline. So when you want to test your new photonic quantum neural network, you can run it side by side with established approaches like quantum kernel methods, quantum reservoir computing, quantum convolutional networks, and more. This is infrastructure. This is the equivalent of what PyTorch and scikit-learn did for classical machine learning, providing a common platform so that instead of saying, my algorithm beats your algorithm on different datasets with different metrics, you can say, my algorithm beats your algorithm on the same benchmark, same metric, same conditions. Now, the second paper. The eighte chapter, and I'll admit, that's a mouthful, is a pedagogical deep dive into entanglement-assisted quantum error-correcting codes. But here's why it matters. Standard quantum.